Hello everyone. So in today's video, we are going to go over this paper titled Civil Rephrases of Toxic Texts with Self-Supervised Transformers. So this paper is by Leo Laguerre, John Pavlopoulos, Jeffrey Sorensen, and Lucas Dixon. So you can see that these are all from top-notch research institutions, and two of them are from Google. So before starting, I'll just like to ask you guys to subscribe to the channel and maybe check out my other videos where I've done some such similar discussions. So I have about 15 videos right now on different types of papers, majorly focusing on NLP and hate speech, but there are some other ones as well. So let's just get right into it. The abstract. Again, a disclaimer, I haven't read this paper myself. This would be the first time I'm doing it with you guys. Platforms that support online commentary from social networks to news sites are increasingly leveraging machine learning to assist their moderation efforts. True, but this process does not typically provide feedback to the author that would help them contribute according to the community guidelines. This is prohibitively time consuming for human moderators to do, and computational approaches are still nascent. This work focuses on models that can help suggest rephrases of toxic comments in a more civil manner. Inspired by recent progress in unpaired sequence-to-sequence tasks, a self-supervised learning model is introduced called CAE-T5. CAE-T5 employs a pre-trained text-to-text transformer which is fine-tuned with a denoising and cyclic autoencoder loss. Experimenting with the largest toxicity detection dataset to date, civil comments, our model generates sentences that are more fluent and better at preserving the initial content compared to earlier textile transfer systems, which we compare with using several scoring systems and human evaluation. So I guess this was pretty self-explanatory. Now let's get into the meat of the paper to understand how they've built the model. So introduction. There are many ways to express our opinions when we exchange views online. We do not always immediately measure the emotional impact of our message. Even when the opinions expressed are legitimate, well intentioned, and constructive, a poor phrasing may make the conversation go awry. Recently, natural language processing research has tackled the problems of abusive language detection by developing accurate classification models that flag toxic or abusive, offensive, hateful comments. Uh, the prospect of healthier conversations nudged by machine learning systems motivates the development of natural language understanding and generation models that could later be integrated in a system suggesting alternatives to vituperative comments before they are posted. So I'm not really familiar with this word. Let's just look it up. So if you followed my other videos, this is what I usually do.
Vituperative.
Vituperative. Alright. A first approach would be to train a text-to-text model on a corpus of parallel comments where each offensive comment has a courteous and fluent rephrasing written by a human annotator. However, such a solution required a large paired label dataset, in practice difficult and expensive to collect. So you might see a problem here because for each hateful message you need a rephrased message. Consequently, we limit our setting to the unsupervised case where the comments are only annotated in attributes related to toxicity, such as the civil comments dataset. We summarize our investigations with the following research question. Can we fine-tune end-to-end a pre-trained text-to-text transformer to suggest civil rephrasings of rude comments using a dataset solely annotated in toxicity? Answering this question might provide researchers with an engineering proof of concept that would enable further exploration of the many complex questions that arise from such a tool being used in conversations. The main contributions of the work are as follows. We address for the second time the task of unsupervised civil rephrases of toxic text, relying for the first time on civil comments dataset and achieving results that reflect the effectiveness of our model over baselines. We developed a non-task specific approach, that is with no human handcrafting in its design, that can be generalized and later applied to relate and or unexplored attribute transfer tasks. So you can see that these are the main contributions of the work. While several of the ideas we combine in our model have been studied independently, to the best of our knowledge, no existing unsupervised model combines sequence to sequence bi-transformers, transfer learning from the large pre-trained models, and self-supervised fine-tuning, denoising, autoencoding, cycle consistency. We discuss the related works introducing these tools and techniques in the following section. So far they've explained why this is important, what they've used, and refer to some works. So let's have a look at this table. Examples of offensive sentences from civil comments tested and the more civil rephrasing generated by a model. The third example shows that its strategy may involve shifting the original intent since Republican is not a synonym, non-offensive synonym of moron. So let me just be back in a second. I'm really sorry. There are lots of disturbances at my current place. So you have the input offensive comment, then you have the generated civil comment. All right. So you can see the problem here, like in the last one. The related work. Unsupervised complex text attribute transfer, like civil rephrasing of toxic comments, remains in its early stages, and a particular applied task has only a single antecedent. There is a great variety of useful works to tackle the task, and this section attempts to summarize the vast majority of those works. We describe below the recent strategies such as attention mechanisms that led to significant progress in supervised NLU and NLG tasks. If you're not familiar with the attention mechanism and you're involved in NLP, I bet you're living under a rock. So, attention mechanisms, for people who haven't seen attention mechanism before, it basically provide some weight to each word. So let's see if we have some good example or an infographic for the attention mechanism, right? Like this. Suppose you have, let me just open this image. In this image, you can see the word animal is closely related to the word it, while the full stop is less closely related. So this is in some sense attention. So this word has more weight to this. So, or if we have some other example, even in the same sentence. So I'll just write one down. I am a boy and I like to play football. Say this is your sentence. Now you can have some links. So I is linked to boy, and uh, this as well. Like to play, the like is also associated with I, not as much as it would be to and. This weight would be lower compared to this weight, and so on. So you get the idea. Transformers are state-of-the-art architectures in NLP. Uh, Vaswani et al. 2017 showed that transformer architectures based on attention mechanisms are achieved state-of-the-art results when applied to supervised neural machine translation. More generally, transformers have proven capable in various NLP and speech tasks. Moreover, transformers benefit from pre-training before being fine-tuned on downstream tasks. Subsequent research has adopted unit transformers in many supervised classification and regression tasks and in unsupervised language modeling. In these works, until it was proposed in this work by Raphael et al., the, they propose a unified pre-trained by transformer applicable to any text classification, text regression, and text-to-text task. Further recent works tackle the language detoxification of unconditional language models. So they've basically described the transformers here and their subsequent modifications. Unsupervised losses enable training text-to-text models end-to-end. After the success of unsupervised image-to-image style transfer in computer vision, some approaches have addressed unsupervised text-to-text tasks. So unsupervised neural machine translation is maybe the most promising of them all. So in these papers, they introduced methods based on techniques aligning the embedding space of monolingual datasets and tricks such as denoising, autoencoding, losses, and back translation. So basically, what they're saying is they're describing text-to-text models and how they are being trained using unsupervised losses. So they mentioned that image-to-image style transfer is there in computer vision. You might have heard about it or even seen some demos for it. So style transfer is basically in context of image to image. You have an image, suppose an image drawn by Picasso, right? And you want to say convert it to an image which retains the same content but is now in the style of Van Gogh. So if there's a man here, then you want to have the man here also, but the drawing should reflect the style of the other painter. So this is a style transfer problem. Alright, so abstract summarization or sentence compression is also studied in unsupervised settings. So Basiotis et al. Trained a model with a compressor reconstructor strategy similar to back translating, while Liu et al. Trained a denoising autoencoder that embeds sentences and paragraphs in a common space. Unsupervised attribute transfer is a task most related to our work. It mainly focuses on sentiment transfer with standard review datasets, but also addresses social linguistic datasets containing text in various registers or with different identity markers. Basically, they're talking about attribute transfer because they want to change the attribute of the sentence. Where they want to change, alter the toxicity and make it more civil. So they say that the previous work has more majorly dealt with sentiment transfer on some standard datasets, but also dealt with some other cases. When paraphrase generation aims at being explicit attribute invariant, it is referred as obfuscation or neutralization. Literally, literary style transfer has also been tackled by recent work. Here we apply attribute transfer to a large dataset annotated in toxicity, but we also use the Yelp review dataset from Shen et al. For comparison purposes. Initial unsupervised attribute transfer approaches sought to build a shared and attribute agnostic latent representation encoding for the input sentence with adversarial training. Then a decoder aware of the destination attribute generated a transferred sentence. So this might seem a lot to take in, but this is basically talking about having a sentence. Let me get some space. So you have a sentence, you pass it through an encoder and you get a vector representation and you try to minimize the style part. So the style should not have significant role in this vector representation, and then it passes through a decoder to give you the output sentence. So this is what was being used, and then you had a discriminator which uh, so you also provided a target style for style transfer, and a discriminator was then used to test the style and give feedback so that the model is able to do the style transfer accurately and so on. So that was adversarial training. Unsupervised attribute transfer approaches that do not rely on a latent space are also present in literature. Lee et al. Assume that the style markers are very local and propose to delete the tokens most conveying the attribute. So we've seen two other papers which built on this paper in the past two videos before retrieving a second sentence in the destination style. They eventually combined both sentences with a neural architecture. In another work, they applied UNMT techniques to several attribute transfer tasks, including social media datasets. In other works, they train models with reinforcement learning. Dye et al. Introduced unsupervised training of a transformer called style transformer with a discriminator network. We've done a video on this. Our approach differs from these unsupervised attribute transfer models in that they did not either leverage large pre-trained transformers or train with denoising objective. The most similar work to ours is Nogueira dos Santos et al. 2018, who trained for the first time an encoder-decoder rewriting offensive sentences in a non-offensive register with non-parallel data from Twitter and Reddit. Our approach differs in the following aspects. First, we use transformers pre-trained on a large corpus instead of randomly initialized RNNs. Second, their approach involves collaborative classifiers to penalize generation when the attribute is not transferred, while we train end-to-end with a denoising autoencoder. Even if their model shows a high accuracy, it suffers from low fluency, with offensive words being replaced by big holders. And underlined by Lampel et al. 2019, applying GANs to NLG is not straightforward because generating text implies a sampling operation that is not differentiable. Consequently, as long as text is represented by discrete tokens, loss gradients computed with a classifier cannot be backpropagated without tricks such as reinforce or the Gumbel softmax. So we've looked at this in previous papers, which can be slow and unstable. Besides, control text generation is an NLG task that consists of a language model conditioned on the attributes of the generated text such as style. But a major difference with attribute transfer is the absence of a constraint regarding the preservation of the input content. So this is how it differs from attribute transfer. You also need to preserve the content when you are rephrasing sentences. So let's have a look at their method. So, formulation of the attribute text rewriting problem. Let xt and xc be two non-parallel corpora of comments satisfying the respective attribute toxic and civil. So X is the total dataset which will have the union of both of them. We aim at learning a parametric function f theta mapping a pair of source sentence X and a destination attribute A to a fluent sentence Y satisfying A and preserving the meaning of X. So basically what they're saying is the function should take in the input sentence and a destination attribute which it should have, and then the output y should have the meaning of x but the attributes of a. So in our case the two attributes are toxic and civil that we assume to be mutually exclusive. We denote alpha x to be the attribute of x and alpha bar x the other attribute. So if it is civil then alpha bar would be toxic. And note that f of x comma alpha x can simply be x. So if it has the same uh, attribute, then suppose if a sentence is civil and you want to rewrite to be civil, then it should of course remain the same. Our approach is based on bidirectional, biconditional encoder decoder generation. Our approach is to train an autoregressive language model continued conditioned on both the input and the input text x and the destination attribute a. So we compute f theta with a language model which computes y based on x and a. As we do not have access to ground truth labels y, we propose in section 3.3 a training function that we do to maximize this. So you do not have any parallel corpus. So for a sentence, you do not have a civil and a toxic version. So that you could just compare it and see the distance between this sentence and the ground label. So in this is why they use other techniques. So they maximize it if and only if y is a fluent sentence with attribute a and preserving x's content. Additionally, they use autoregressive generating model, which in where inference of y is sequential and the token generated at step t plus 1 depends on the token at the previous steps. So suppose you're generating a sentence. Let me just get some space. And you've so far written I am a, and then you want to predict the next word, then these words also provide context to the prediction of this word. Alright, so to condition on the input text, we follow the work of all these works and opt for an encoder decoder framework. In Lampel and Diet al. They argue that in unsupervised attribute rewriting tasks, encoder do not necessarily output disentangled representation independent of its attribute. However, the TSNE visualization of the latent space allowed us to assume the encoders can output a latent representation Z attending to content rather than on attribute with a similar training. So basically what they're saying in these two works, it was said that this latent space representation does not necessarily uh, become attribute free. So it's not content only. However, the TSNE visualization, so TSNE is a kind of visualization. If you've seen some of these, I'll just show you a plot. So of course this is stat quest videos are the best, but you can see, right? So you in this TSNE plot you can see The different uh, only two dimensions are there, and how for the MNIST dataset where you have those handwritten labels, you can see how distinctly the clusters are formed. So basically, they're saying using this visualization of the latent space in the work by Liu et al. They it allowed them to assume that the latent representation is attending to content rather than the attribute. So it is more focusing on the message and not the style of the message. The language model is conditioned on the destination attribute with control codes. A control code is a fixed sequence of tokens prepended to the decoder's input and supposed to prepare the generation in the space of sentences with the destination attribute A. Alright, so basically what they're saying is they have control codes. Control codes are nothing but sequences which they add to the decoder's input. So this is going into the decoder, they add it here, and uh, this helps, and they are supposed to prepare the generation in the space of sentences with the destination attribute A. So you add the control code for a particular attribute. So they define gamma A comma S. So A is the attribute, S is the decoder input, which is effectively concatenate S with C of A, where C of A is the control code attribute of A. So basically you have a control code for an attribute and you just add it to the input to the vector. So you'll have this control code which will be added here. Alright. Training the encoder decoder with an unsupervised objective. Denoising objectives to train transformers are an effective self-supervised strategy. Denoising objectives to train transformers are an effective self-supervised strategy. In these works, they pre-train the unit transformer encoder as a masked language model to teach the system general-purpose representations before fine-tuning on downstream tasks. Alright, this was a lot to take in. I'll just read this again. So they are training they are now discussing the training of the encoder decoder with an unsupervised objective. Unsupervised basically means like literally not supervising it. So denoising objectives to train transformers are an effective self-supervised strategy. All right. In these two works by Delvin and Yang et al., they pre-trained a uni-transformer encoder as a masked language model to teach the system general-purpose representations before fine-tuning on downstream tasks. So a masked language model is basically where training happens by masking words. So suppose you have this sentence: I am a boy and I like to jump on the trampoline, right? So suppose you have this sentence. So while training it in a masked language model, you will hide words. Suppose you hide this word jump and ask the model to see all of the words around it and predict which word should fit here. Then the model will predict something, then you'll tell it no, this should have been there, then it will try to minimize the error and so on. Similarly, you might hide the word boy or the word trampoline and so on. So I guess that makes sense. Then we have these works by Kono and Lampel et al., Song et al., Liu et al., and Raphael et al. They explore various de-shuffling and denoising objectives to pre-train or fine-tune biotransformers. So during training, we corrupt the encoder's input X with a noise function. So basically, you add noise because in the real world you will have that noise. Eta mask tokens randomly with probability 15%. Then masks are replaced by a random token in the vocabulary with probability 10% and left as a sentinel with probability 90%. We train the model as denoising autoencoder, meaning that we minimize the negative log likelihood of this. The hypothesis is that optimizing the DAE objective teaches the control generation of the model. Inspired by an equivalent approach in unsupervised image-to-image style transfer, we add a cycle consistency objective. Alright, which enforces content preservation. So cycle consistency is basically taking a sentence, say you have a civil sentence, you make it toxic, then you make it back civil. And so the original civil and the generated civil should ideally be the same, but you will know that is not the case. So you tend to minimize the distance between the two by using some objective, which is a cycle consistency objective. As a cycle consistency objective, computes a non-differentiable autoregressive pseudo-prediction had during stochastic gradient descent training. Gradients are not backpropagated at training step tau. Finally, the loss function sums the dE and the CC with some coefficients. So this loss function is basically the loss function of training this denoising autoencoder. The denoising autoencoder is nothing but you add noise and the autoencoder learns to remove that noise. As simple as that. The word denoising. So how do you add noise? You mask tokens, you replace them with random words, and you add some noise. The text-to-text biotransformer architecture. The architectures for the encoder and decoder are unitransformers, contrary to Vaswani et al., Kono and Lampel, Raphael et al. We do not keep decoders layer computing cross attention between the encoder's output edge and the decoder hidden variable because generation suffers from too much conditioning on the input sentence and we observe no significant change in the output sentence. Alright, that was again a lot to take in. Let's just read it again sentence by sentence. The architectures for the encoder and decoder are unit transformers. So I presume that means they have a single transformer. Contrary to these works, we do not keep the decoder's layer computing cross attention between the encoder's output edge and the decoder hidden variable because generation suffers from too much conditioning on the input sentence and we observe no significant change in the output sentence. So in the traditional transformer architecture, they had this cross attention mechanism which they say leads to no the input sentence having more weightage in the output sentence, so the output will have no significant change. So that is why they do not keep it. Rather, they follow this work by Liu et al. And compute the latent representation with an affine transformation of the encoder's hidden state H naught corresponding to the first token of the input text. So an affine transformation, I forgot the meaning. Let's just look it up. Affine transformation is a transformation that uh, preserves collinearity. So combines linear transformations and translations. All right, makes sense. So they have the latent representation Z, which was uh, this representation. If you go up in the encoder decoder architecture, this is the latent representation. And they do some affine transformations on it. And uh, okay, no, sorry. They are computing the latent representation with affine transformation of the encoder hidden state. So the encoder's hidden state, the first hidden state, which was for the first token, that is changed. So let x belonging to capital X be the input sequence of token. It is embedded then encoded by the univ transformer encoder. So first of all, you create an embedding, then you encode it, and then its first value is picked up, which is then passed through a function to get the latent space representation. So Z is an aggregate sequence representation for the input. There are different heuristics that can be used to integrate it in the decoder. We considered summing Z to the embeddings of each token of the unit transformer decoder input S, since it balances the back propagation of signal coming from the original input and from the output being generated in the destination attribute space, and it worked well in the practice in our experiments. So basically they took this gamma AS. So let's just go back to visit what gamma AS was. We were adding this control code to the sentence. So the decoder input had this control code. So first you compute that and get the gamma embedding. And inside this gamma embedding you add Z, which is your latent space representation. And then encode it to get the hidden space representation of the decoder. Then this goes to the language model which generates the sentence. Plus, the encoder and decoder unit transformers share the same embedding layer, and the language model head is tied to the embeddings. Except for the dense layer computing the latent variables Z, all parameters are coming from the pre-trained biotransformers published by these works. Thus, our DAE and CC objectives fine-tune T5's parameters, and this is why we call our model a conditional autoencoder text-to-text transformer. So CAE E is conditional autoencoder, and T5 is this text-to-text transformer. So I hope you got this part. Now moving on to their experiments. So we employed the largest publicly available toxicity detection dataset to date, which was using the Jigsaw unintended bias in toxicity classification Kaggle challenge. The 2 million comments of the civil comments dataset stem from commenting plugins for independent news site. They were created from 2015 to 2017 and appeared on approximately 50 English language news sites across the world. Each of these comments are annotated by the crowd for toxicity and toxicity subtype. Following the work of Dye et al. For the IMDb movie review dataset, we constructed a sentence-level version of the dataset. So initially we fine-tuned the pre-trained word toxicity classifier on the civil comment dataset. Then we split the comments in sentences with NLTK sentence tokenizer. Eventually we created X3 and respectively X3 with sentences whose system-generated toxicity score using our word classifier is greater than zero point 0.9, respectively less than zero point 0.1, to increase the dataset's polarity. The test ROC-AUC of the toxicity classifier is 0.98 with a precision of 0.95 and a recall of 0.38. Even with this low recall, XT is large enough. So basically what they're saying is, since the IMDb reviews dataset might contain paragraphs, so they use the NLTK sentence tokenizer to break it into sentences, and then they used uh, the BERT classifier to classify it as toxic or civil. And if it was uh, greater than zero point 0.9 toxicity, or if the civil toxicity was less than zero point 0.1, then it went to toxic or civil respectively. Then they checked the ROC and AUC of the toxicity classifier, which was very high. So the recall was low, but even with the low recall, it's a pretty large data set. We also conduct a comparison to other style transfer baselines on the Yelp review dataset, and it consists of restaurant reviews. All right. So evaluation. Evaluating a text-to-text task is challenging, especially when no gold pairs are available. Attribute transference is successful if generated text has the destination, so control attribute is fluent and preserves the content of the input text. So these are the three major parameters. So for automatic evaluation, they check the AC attribute control accuracy. So accuracy ACC computes the rate of successful change in attributes. It measures how well the generation is conditioned by the destination attribute. We predict toxic and civil attributes with the same fine-tuned bot classifier that pre-processes the civil comments dataset. For fluency, it's measured by perplexity. To measure PPL, they employ GPT-2 language model fine-tuned to the corresponding dataset. All right. For content preservation, it's difficult to measure. You might also guess so because even as humans, it would be difficult to do so. UNMT summarization and sentiment transfer have access to few hundred samples with at least one human reference of the transferred text and evaluate content preservation by computing metrics based on machine words between the generated prediction and the references. However, as we do not have these paired samples, we compute a content preservation score between the input and the generated sentence. So table 3 shows the blue scores based on exact matching. In the topmost example, blue score is high. This is explained by the fact that only four words are different. In contrast, to the first example, the two texts in the second example have only one word, so the blue score is low. So it's at 3.4. Despite the low evaluation, however, the candidate text could have been a valid rephrase of the reference text. So basically, what they're saying is a blue score is not a good metric because sometimes you do not really need to retain the words. You also need to make some changes. The high complexity of a task explains the motivation for a more general quantitative metric between input and generated text, capturing the semantic similarity rather than overlapping tokens. So in these works, they propose to represent sentences as weighted average of their word embeddings before computing the cosine similarity between them. We adopted a similar strategy, but we embedded sentences with a universal sentence encoder and call it sentence similarity score. The first two sentences of pair 3 have high similarity score. The rephrasings preserve the original content while not alright. However, the last rephrasing does not preserve the initial content and has a low similarity score. As a statistical evidence, the self-SIM score comparing each of the 1,000 Yelp reviews with their human writing is 80.2%, while the self-SIM score comparing the Yelp review tested to a random one is 36.8%. So you can see the self-SIM score works. We've also seen this work score being adapted in other works in the future. We optimize all three metrics because doing otherwise comes at the expense of the remaining metrics. We aggregated the score of the three by computing the geometric mean of all of these. So you can see the SIM is higher for ones where even when the blue is lower, if it was a valid one. So for human evaluation, they hired human annotators on append to rate in a blind fashion different models, civil rephrasing of 100 randomly selected text toxic comments in terms of attribute transfer, fluency, content, and overall quality. Each rephrasing was annotated by 5 different crowd workers whose annotation quality is controlled by test questions. If a rephrasing is successful, then on all three, then it is successful. So the baselines. We compare the output that CAE-T5 generates with a selection of unpaired models. We also compare with input masking. It is inspired by the interpretability model called input erasure. IE is used to interpret the decision of neural model. Initially, words are removed one at a time and then altered texts are then reclassified. Then all words that lead to a decreased reclassification score are returned as one most related to the decision of the neural model. Our baseline follows a similar process, but instead of deleting, they mask it. When all the mask tokens have been scored by the classifier, the rephrased text is returned, comprising as many masks as tokens that led to the decreased reclassification score. We employed a pre-trained BERT model. Alright, so I guess this is pretty clear enough on how IE works and how they adapted it. So instead of deleting the words, they just masked it. Either way, the machine cannot see it. So the results. Quantitative comparisons to prior work. So they've shown the comparisons to prior work. Surprisingly, the perplexity capturing fluency of text generated by our model is lower than those by computer and human comments. This can be explained by social media authors of comments expressing an important variability in language formal rules that is only partially replicated by CAE-T5. Other approaches such as style transform and cross alignment have higher accuracy but at a cost of both higher perplexity and lower content preservation. So you can see the perplexity is much higher and the content preservation is also lower. In table 5, we compare our model to prior work in attribute transfer by computing evaluation metrics for different systems. We achieve competitive result with low perplexity while getting good sentiment controlling. Our similarity though is lower, showing that that some content is lost. Hence the latent space does not fully capture the semantics. It is fairer to compare our model to other style transfer baselines on the Yelp dataset since our model is based on sub word tokenization, while the baselines are often based on a limited size pre-trained word embedding. Many more words from the civil comment dataset could be attributed to the unknown tokens if we want to keep reasonable size vocabulary resulting in a performance drop. Alright, so basically they justifying uh, why some models have why they have lower perplexity in the first half, and then they're justifying why they can compare on the same data set. So it is fairer to compare our model to other style transfer baselines since our model is so and so. The human evaluation results shown in table 6 correlate with automatic evaluation results. When considering the aggregated scores, our model is ranked first on the civil comments dataset and ranked second on the Yelp review dataset behind dual RL, yet our approach is more stable and therefore easier to train when compared to reinforcement learning approaches. So dual RL is a reinforcement learning approach, I presume. Now for qualitative analysis, I guess these are being shown here. Right. Table 7 shows examples of rephrases. The top first two examples emphasize the ability for the model to perform fluent control generation condition on both input and destination attribute. We present more results showing that we can fluently rephrase sentences. However, we observe more failures on the sentiment transfer tasks. So supererogation generation does not stop early enough and produce fluent transfer related but unnecessary content. So these are the reason of failure. Hallucination is the model generates fluent but unrelated content, and position reversal, the author's opinion is shifted. In order to assess the frequency of hallucination and supererogation, we randomly selected 100 toxic spans under tested and manually labeled them. So 17% had supererogation, 34% suffered from hallucination, mostly local. We observed that the longer the inputs comment, the more prone to hallucination the generated text is. Alright. When supererogation hallucination can be explained by the probabilistic nature of generation because each token has a probability of appearing. Uh, so it's not totally that the model knows how to speak. It's predicting what should be coming after it. We assume that the Persian reversal is due to bias in the dataset where toxic comments are correlated with negative comments. So most of them might have one leaning. Thus, offensive comments tend to be transferred to supportive comments even though a human being would rephrase attacks as polite disagreements. True. Interestingly, our model is able to add toxicity in civil comments. Even if such an application shows limited interest for online platforms, it's worth warning about its potential misuse. True, because then someone might pick up civil comments and make them offensive. So the discussion, we'll have a look at the so stop being ignorant and lazy and try reading a bit about it. Try reading and be a little more informed about it before you try to make a comment. So this is a valid rewriting. These are supererogation, coercion retrieval, and hallucination. Alright. So you can have a look at the examples. You can also have a look at the scores. Alright, so the discussion. Supervised learning is a natural approach when addressing text to text tasks. In our study, we submit the civil rephrasing of toxic comments task to human crowdsourcing. We randomly sampled 500 sentences. For each sentence, they asked 5 annotators to assess if it was offensive and if it was possible to rewrite it in a rude way. On 2500 answers, we tally 427 examples not flagged as impossible to write and with a rephrasing different from the original sentence. This low 17.1% yield is caused by two main issues. On the one hand, unfortunately, not all toxic comments can be reworded in a civil manner so as to express a constructive point of view. Severely toxic comments that are solely made of insults, identity attacks, or threats are not rephrasable. True. On the other hand, evaluating crowd workers with text questions and answers is complex. The perplexity being higher on crowd workers rephrases than on randomly sampled civil comments raises concerns about the production of human references by crowdsourcing. So they're questioning the method of evaluation. The nature of large datasets labeled in toxicity and the lack of incentives for crowdsourcing civil rephrasing annotations makes it expensive and difficult to train systems in a supervised framework. These limitations motivates unsupervised approaches. Lastly, the more complex is the unsupervised attribute transfer task, the more difficult is its automatic evaluation. In our case, evaluating whether the attribute is actually transferred is used by an accurate toxicity classifier. Furthermore, the language model we use to assess the fluency of the generated sentence has some limitation, does not generalize to all varieties of language encountered. Finally, measuring the amount of relevant content preserved between the source and generated text remains a challenging open research topic. Alright. So conclusions. This work is the second one to tackle civil rephrasing to our knowledge and the first one to address it in a fully end-to-end discriminator-free text-to-text self-supervised learning. CAE-T5 leverages the NLU-NLG power offered by large pre-trained biotransformers. The qualitative and quantitative and qualitative analysis shows that ML systems could contribute to some extent to pacify online conversations. So you might see the usage, right? Someone might be very angry in a fit of rage, might be writing something, and he gets a prompt. Maybe you would like to rephrase it like this, and then he maybe even then he might even drop the idea and realizing his mistake. In the future, we plan to explore whether the decoding can benefit from NAR regeneration. We also are interested in the recent paradigm shift proposed by Kumar and Svetkov, where the generated tokens representation is continuous, allowing more flexibility in plugging attribute classifiers without sampling. Alright. So this was the future direction. Let's have a look at the okay. So they mentioned the learning algorithm and the architecture. So this is what we saw earlier. They then mention how they trained it. They use ADA factor optimization. They use a TPV2 chip. Then they mentioned their constants. I guess you can read this up because this is hidden trial. They also mentioned the settings. Then this is a model architecture, unit transformer systems, and then they have their examples. But since they might be offensive, so I'm not going to read them. But you can certainly read them. This is the uh, form which was shown to the crowd workers. So again, thank you guys for joining in. This was a pretty good paper to read, and maybe I'll be off for a bit now. But thank you again. Please do like, share, and subscribe. And as always, if you have any comment, do not hesitate to uh, point out any mistakes and share any criticism. So thank you guys for tuning in. Hope to see you the next time.